All right, guys, here we go. Just setting up some final little configurations here. About to get started. All right, guys. I am extremely excited for tonight's stream. The conversation between Lex Fridman and Frank Wilcezk, I think it's pronounced, is really cool because they obviously get into some technical aspects of physics, mathematics, nature of the universe and stuff. But this conversation gets like very philosophical at some point, and they, talk about some of the larger problems, not just with science in general, but just man's capacity to actually understand the depth and the complexity of the world that we're in. So we're gonna let Lex do his intro. As always, I am also gonna let him run his little ad spiel, and we'll just be kind of pausing and going talking as we go here. So guys, please enjoy, and thanks for joining.
The following is a conversation with Frank Wilcezk, a theoretical physicist at MIT who won the Nobel Prize for the co-discovery of asymptotic freedom in the theory of strong interaction. Quick mention of our sponsors, The Information, NetSuite, ExpressVPN, Blinkist, and Sleep. Check them out in the description to support this podcast. As a side note, let me say a word about asymptotic freedom. Protons and neutrons make up the nucleus of an atom. Strong interaction is responsible for the strong nuclear force that binds them. But strong interaction also holds together the quarks that make up the protons and neutrons. Frank Wilcezk, David Gross, and David Pulitzer came up with a theory postulating that when quarks come really close to one another, the attraction abates and they behave like free particles. This is called asymptotic freedom. This happens at very, very high energies, which is also where all the fun is. This is the Lex Fridman podcast, and here is my conversation with Frank Wilcezk. What is the most beautiful idea in physics?
The most beautiful idea in physics is that we can get a compact description of the world that's very precise and very full at the level of the operating system of the world. That's an extraordinary gift, and we get worried when we find discrepancies between our description of the world and what's actually observed at the level even of a part in a billion.
You actually have this quote from Einstein that the most incomprehensible thing about the universe is that it is comprehensible, something like that.
Yes, that's the most beautiful surprise that I think that really was to me the most profound result of the scientific revolution of the 17th century, with the shining example of Newtonian physics, that you could aspire to completeness, precision, and a concise description of the world, of the operating system. And it's gotten better and better over the years, and that's the continuing miracle. Now, there are a lot of beautiful sub-miracles too. The form of the equations is governed by high degrees of symmetry, and they have very surprising kind of mind-expanding structure, especially in quantum mechanics. But if I had to say the single most beautiful revelation is that, in fact, the world is comprehensible.
Would you say?
So there's something I want to touch on with just like what he said there. It is fascinating that I think Dr. Lawrence Krauss kind of hits on this topic in a lot of the conversations and interviews that he has, that like the human brain was not evolved to understand that we are like on a ball of rock floating through the universe, and how big the universe is, and it's expanding, and it has dark matter. Like, that's not really the evolution, or was not necessarily the evolutionary path of what our brains were built to do, you know, as like sort of hunter-gatherers from an evolutionary perspective. You know, our hardware and software was really based off of the basic needs, you know, getting food, shelter, surviving, and it's through our ability to cooperate as human beings, form civilizations and societies, and to be able to achieve things like higher thinking, which is another beautiful thing about life.
Say that's a fact or a hope?
It's a fact. You can point to things like the rise of gross national products, per capita around the world as a result of the scientific revolution. You can see it all around you in recent developments with exponential production of wealth, control of nature at a very profound level, where we do things like sense tiny vibrations to tell that there are black holes colliding far away,
So what he's referring to there is the LIGO detector. LIGO are two of these like incredibly, they're some of the most precise instruments that we've actually built in just like human civilization. They're essentially, it's an L-shaped laser, where they shoot a laser one way and they shoot a laser another way, and they use prisms to measure the deviation of that laser. And these two detectors are actually set up on either side of like the continent of North America, and the reason for that is so that they can actually detect the gravitational wave moving, you know, across space and time. And a couple of years ago, LIGO, which we set up was able to detect the first ever detected gravitational wave that actually passed through Earth. And when they traced that back, it actually came from two black holes colliding. So that's what he's referring to when he talks about the detection of gravitational waves.
Test laws, as I alluded to, as a part in a billion, and do things in what appear on the surface to be entirely different conceptual universes. I mean, on the one hand, pencil and paper, or nowadays computers that calculate abstractions, and on the other hand, magnets and accelerators and detectors that look at the behavior of fundamental particles. And these different universes have to agree, or else we get very upset. And
so what he's referring to is I've talked about this a couple of times, but the major current problem in physics, and I think they talk about this at the end, theory of everything. We have the rules of physics that govern the things that are very large. Like, we understand how gravity impacts, the way the Earth goes around the sun. We know how gravity works on the planet Earth. But as we take the scale of matter smaller and smaller, the rules of the very large do not apply to the rules of the very small, the quantum. This is a huge problem in physics that we have tried to bridge through string theory, grand unification theory, M theory. No one has really come up with a competent or likely solution at this point, but that's what he's referring to here.
That's it's an amazing thing if you think about it. So, and it's telling us that we do understand a lot about nature at a very profound level, and there are still things we don't understand, of course, but as we get better and better answers and better ability to address difficult questions, we can ask more and more ambitious questions.
Something that when I first started watching this interview that really resonated with me, a lot of people say, well, we don't know how we know science knows a lot, but there's a lot that we don't know. And that essentially is true. There's an enormous amount of things that we do not know about how the universe works and the underlying structure of it. But we do know quite a bit. And what we know gives us a very solid foothold of, these are the rules, these are how things that we can figure out seem to work. And from that, we can extrapolate a lot of possibilities about what the borders of those rules are. And I think that's where something that upsets me when people are not necessarily as scientifically literate say, oh, we don't know a lot of stuff. Well, yeah, there's definitely like huge gaps of knowledge. But in terms of a framework for all things, understanding how things very large, things very small work, we have a robust understanding and framework for how to piece those things together.
Well, I guess the hope part of that is because we are surrounded by mystery. So one way to say it, if you look at the growth of the GDP, over time that we figured out quite a lot, and we're able to improve the quality of life because of that, and we've figured out some fundamental things about this universe, but we still don't know how much mystery there is. And it's also possible that there's some things that are in fact incomprehensible to both our minds and the tools of science. Like the sad thing is we may not know it because in fact they are incomprehensible. And that's the open question, is how much of the universe is comprehensible? If we figured out the everything, what's inside the black hole and everything that happened at the moment of the Big Bang, does that still give us the key to understanding the human mind and the emergence of all the beautiful complexity we see around us? That's not like when I see these objects, like I don't know if you've seen them, like cellular automata, all these kinds of objects where from simple rules emerges complexity.
Yes.
It makes you wonder, maybe it's not reducible to simple, beautiful equations.
Subject,
the whole
good to see you,
thing,
bud.
only parts of it.
So we got to look at cellular automaton because they touched on this really quick, and it is an absolutely fascinating. Cellular automata was I think it was a concept that was pioneered by Stephen Wolfram, and essentially the idea here is that they, if you create a grid pattern and you set up a set of rules, saying that, well, if there's a black square here and there's a black square here, there should be two white squares here. But if there's two, black squares here, there should be two white squares here, and so on and so forth. So you can set a basis of rules up. And depending on how you change the rules, you see different levels of varying either order or complexity. The point of this is that the subtlest, tiniest changes in this rule set can either give you something, and these are some great pattern examples, where you get like these nice ordered triangles. Sometimes you see stuff with a bunch of randomness in it. So a lot of the pursuit in understanding nature is trying to boil things down to their most simplest constituent elements. So having equations that are super simple and elegant that explain where all of the complexity and the diversity of our universe comes from. And we can see this phenomenon very well illustrated in something simple like cellular automatons. So you can see how tiny, minuscule changes in a system can have drastic impact. There's another great video that we might touch on later around this, but let's keep diving.
That's the tension I was getting at with the hope.
Well, when we say the universe is comprehensible, we have to kind of draw careful distinctions about, or definitions about what we mean by that.
Both the universe and the comprehensible.
Exactly, right. So in certain areas of understanding reality, we've made extraordinary progress, I would say, in understanding fundamental physical processes and getting very precise equations that really work and allow us to do the profound sculpting of matter, to make computers and iPhones and everything else, and they really work, and they're extraordinary productions. On the other, but that's all based on the laws of quantum mechanics, and they really work, and that.
So the point that he's trying to make here is. Oh, no worries, dude. Always just you pop in and out as you need, man. This is always fun to have people dropping in and out as they go. The point that he's trying to make here, which I find super fascinating, is that when people talk about science and our understanding of the universe and physics, you can't. Like the most perfect example is this, your iPhone or your computer. The whole, because of the way we understand electrons and their ability to manipulate them, gives us an insane amount of precision to be able to essentially do things like computing and have technology. So our understanding of these processes is it's directly correlated to the technology that we all get to use every day. So when people think that why are we studying quarks and energy and all these other things, it's because that's going to be the future of how our computers work and how the technology that makes our lives better is going to work and how we're going to generate electricity and all these other fun things. So
and they give us tremendous control of nature. On the other hand, as I say, as we get better answers, we can also ask more ambitious questions. And there are certainly things that have been observed, even in what would be usually called the realm of physics, that aren't understood. For instance, there seems to be another source of mass in the universe, the so-called dark matter, that we don't know what it is, and it's a very interesting question what it is. But also, as you were alluding to, it's one thing to know the basic equations. It's another thing to be able to solve them in important cases. So we run up against the limits of that in things like chemistry, where we'd like to be able to design molecules and predict their behavior from the equations. We think the equations could do that in principle, but in practice, it's very challenging to solve them in all but very simple cases. And then there's the other thing, which is that a lot of what we're interested in is historically conditioned. It's not a matter of the fundamental equations, but about what has evolved or come out of the early universe and formed into people and frogs and societies and things. And the laws of physics, the basic laws of physics, only take you so far. in that it kind of provides a foundation, but doesn't really. You need entirely different concepts to deal with those kind of systems, and
So they deal with this in like fluid dynamics and thermodynamics as well, in the sense that if you have a if you have a chamber full of gas, right, you can predict the pressures and the way those gases are going to move and interact, but because of the level of like quantum jitter, just general randomness, and our inability to map every single molecule or atom and its interaction, we'll never be able to with 100% accuracy predict exactly how it's going to behave or exactly how that cloud chamber is going to look. And so that is the interesting disconnect between these incredibly powerful laws of physics that allow us to get like deep, meaningful insight in the world, and how we can point them at very specific things and see them. But when you start to try and scope it out and say, to his point, like, okay, so we know how the universe formed, but how did frogs and trees and everything come about? And it's like, well, that is really testing the limits of our knowledge and how we tie those things together.
all we one thing I can say about that is that the laws themselves point out their limitations, that they kind of, they're laws for dynamical evolution. So they tell you what happens if you have a certain starting point, but they don't tell you what the starting point should be, at least. Yeah. And the other thing that emerges from the equations themselves is the phenomena of chaos and sensitivity to initial conditions, which tells us that that there are intrinsic limitations on how well we can spell out the consequences of the laws if we try to apply them.
It's the old apple pie. If you want to, what is it, make an apple pie from scratch, you have to build the universe or something like that.
Well, you're much better off starting with apples than starting with quarks. Let's put it that way.
In your book, A Beautiful Question, you ask, does the world embody beautiful ideas? So the book is centered around this very interesting question. It's like Shakespeare. You can like dig in and read into all the different interpretations of this question. But at the high level, what to you is the connection between beauty of the world and physics of the world?
In a sense, we now have a lot of insight into what the laws are, the form they take, that allow us to understand matter in great depth and control it, as we've discussed. And it's an extraordinary thing how mathematically ideal those equations turn out to be. In the early days of Greek philosophy, Plato had this model of atoms built out of the 5 perfectly symmetrical Platonic solids. So there was somehow the idea that mathematical symmetry should govern the world. And we've out-Platoed Plato by far in modern physics, because we have symmetries that are much more extensive, much more powerful, that turn out to be the ingredients out of which we construct our theory of the world. And it works. And so that's certainly beautiful. So the idea of symmetry, which is a driving inspiration in much of human art, especially decorative art, like the Alhambra, or in wallpaper designs, or things you see around you everywhere, also turns out to be the dominant theme in modern fundamental physics.
So symmetry is such a fascinating concept, and I get really excited talking about it because, to his point, like, it is symmetry that draws our aesthetic liking. You know, when you hear a particular piece of music, the wavelengths of all that noise, there's a symmetry to it that just like really resonates with your body. When you see a piece of art, you're like, wow, I think that's really cool. You know, the concept of symmetry in art also exists in physics. Whether or not you get as stoked as this guy does on the equations and their forms and just how beautifully simplistic and symmetrical they are, or just the actual concept of symmetry, like, for example, the symmetry between an object and its shadow on the wall. You might have a huge shadow, but the actual object projecting it might be tiny. But there's a symmetry between those two things, right? The consistency that binds them. It truly is like a beautiful concept.
Symmetry and its manifestations, because the laws turn out to have these tremendous amounts of symmetry. You can change the symbols and move them around in different ways, and they still have the same consequences. So that's beautiful, and these things, these concepts that humans find appealing also turn out to be the concepts that govern how the world actually works. And I don't think that's an accident. I think humans were evolved to be able to interact with the world in ways that are advantageous and to learn from it. And so we are naturally evolved or designed to enjoy beauty and to symmetry, and the world has it, and that's why we resonate with it.
Well, it's interesting that the ideas of symmetry emerge at many levels of the hierarchy of the universe. So you're talking about particles, but it also is at the level of chemistry and biology and
like, even when you look at like molecules and different like formations of compounds, and you see how they organize yourself, you do see these beautiful patterns and these symmetries. Like, if you look at like here, let's look at a fractal GIF. If you look at sort of like these moving fractal images, right? It's just an image inside of an image inside of an image that's repeated over and over and over again. It's these symmetries in nature, and a lot of people find these patterns to be particularly soothing, or you get drawn into them, and it's just it's our. I guess that what I'm trying to say is, my argument would be, a lot of our love for art and beauty and just the things that make us feel good in the world come from an attachment to symmetry, and that's naturally born just out of the way the world works.
And the fact that our cognitive, sort of our perception system and whatever our cognition is, also finds it appealing, or somehow our sense of what is beautiful is grounded in this idea of symmetry, or the breaking of symmetry. Yeah. Symmetry is at the core of our conception of beauty, whether it's the breaking or the non-breaking of the symmetry. Yes. It makes you wonder why. Like, so I come from Russia, and the question of Dostoevsky, he has said that beauty will save the world. Maybe as a physicist, you can tell me, what do you think he meant by that?
I don't know if it saves the world, but it does turn out to be a tremendous source of insight into the world when we investigate kind of the most fundamental interactions, things that are hard to access because they occur at very short distances between very special kinds of particles whose properties are only revealed at high energies. We don't have much to go on from everyday life, but so we have, when we guess what and the experiments are difficult to do, so you can't really follow a very wholly empirical procedure to sort of, in the Baconian style, figure out the laws kind of step by step, just by accumulating a lot of data. What we actually do is guess, and the guesses are kind of aesthetic, really. What would be a nice description that's consistent with what we know, and then you try it out and see if it works, and by gosh.
I mean, you can't tell me that the way that man just described that, and almost like his energy, is not what you would hear from like a jazz musician. It's like, well, we didn't really know what to do. We just played the instrument. We tried some notes. We experimented. We stabbed at things. And this is where that drawing between the symmetry of nature and our proclivity to kind of chase that, it makes sense.
It does in many profound cases. So there's that, but there's another source of symmetry which I didn't talk so much about in A Beautiful Question, but does relate to your comments, and I think very much relates to the source of symmetry that we find in biology and in our heads, you know, in our brain, which is that although it is discussed a bit in A Beautiful Question and also in Fundamentals, is that when you have symmetry is also a very important means of construction. So when you have, for instance, simple viruses that need to construct their coat, their protein coat, the coats often take the form of platonic solids. And the reason is that the viruses are really dumb and they only know how to do one thing. So they make a pentagon, then they make another pentagon, and they make another pentagon, and they all glue together in the same way, and that makes a very symmetrical object, sort of. So the rules of development, when you have simple rules and they work again and again, you get symmetrical patterns.
So I'm actually going to show you guys a really interesting visualization of what he's talking about. So give me 1 second. The limit of math, is it? Well, let's go to my... I was just watching this. Math's fatal flaw. Okay, so I talked very briefly, some of you weren't here for it, about cellular automata, which are essentially just like little programs with very simple rules. And based off of the rules, a little game plays out. So this is a really good description of what it looks like, and I think you'll be able to draw the connection between what we're talking about here and perhaps where the emergence of life comes from.
Once you've set up the initial arrangement of cells, the two rules are applied to create and two dead cell with a Conway's game of life is played on an infinite grid of square cells, each of which is either live or dead. And there are only two rules. 1, any dead cell with exactly 3 neighbors comes to life. And 2, any living cell with less than 2 or more than 3 neighbors dies. Once you've set up the initial arrangement of cells, the two rules are applied to create the next generation, and then the one after that, and the one after that, and so on.
Okay, watch this.
It's totally automatic. Conway called it a 0-player game. But even though the rules are simple, the game itself can generate a wide variety of behavior. Some patterns are stable. Once they arise, they never change. Others oscillate back and forth in a loop. A few can travel across the grid forever, like this.
So, like, if I look at these, the connection that I make is like that's what like proteins are like in your body. That's like the most fundamental building block. Like how those proteins behave and move and do their different little function is probably determined by incredibly small changes in some fundamental building blocks.
This glider here. Many patterns just fizzle out. But a few keep growing forever. They keep generating new cells. Now, you would think that given the simple rules of the game, you could just look at any pattern and determine what will happen to it. Will it eventually reach a steady state?
Okay, so we're not going to go too deep into this. We're going to
It's kind of, in fact, it's a recipe also for generating fractals. You know, like a kind of broccoli that has all this internal structure, and I wish I had a picture to show, but maybe people remember it from the supermarket, and you say, how did a vegetable get so intelligent to make such a beautiful object with all this fractal structure? And the secret is stupidity. You just do the same thing over and over again, and in our brain,
which, by the way, is a property that is shared with artificial intelligence, is that it is just a very simple set of rules that is changing, making small incremental changes, and then repeating those millions of times. So when you think about like what AI and what they're doing, it's essentially like a petri dish for potential intelligence.
Brains also, we start from single cells, and they reproduce, and they're each one does basically roughly the same thing. The program evolves in time, of course. Different different modules get turned on and off. Different regions of the genetic code get turned on and off, but basically a lot of the same things are going on, and they're simple things, and so you produce the same patterns over and over again, and that's a recipe for producing symmetry, because you're getting the same thing in many places. And if you look at, for instance, the beautiful drawings of Ramon y Cajal, the great neuroanatomist, who drew the structure of different organs like the hippocampus, you see it's very regular and very intricate, and it's symmetry in that sense. It's because it's many repeated units that you can take from one place to the other and see that they look more or less the same.
But what you're describing, this kind of beauty that we're talking about now, is a very small sample in terms of space-time in a very big world, in a very short, brief moment in this long history. In your book, Fundamentals: 10 Keys to Reality,
100% fucking
I'd
mushrooms
recommend
all the
people read
time.
it.
There's no question.
You you say that space and time are pretty big, or very big. How big are we talking about? Like what? Can you tell a brief history of space and time?
It's easy to tell a brief history, but the details get very involved, of course. But one thing I like to say is that if you take a broad enough view, the history of the universe is simpler than the history of Sweden, say, because your standards are lower for but just to make it quantitative, I'll just give a few highlights, and it's a little bit easier to talk about time. So let's start with that. The Big Bang occurred. We think the universe was much hotter and denser and more uniform about 13.8 billion years ago. That's what we call the Big Bang.
So from our understanding of where the universe is now, if you follow the rules back, we believe that it all started from a single point of super condensed energy, exploded, and thus that's what we have today.
And it's been expanding and cooling. The matter in it has been expanding and cooling.
Accelerating too. That's something that some people really don't realize, that it's not only is the universe, like when you see an explosion in like MacGruber and the boat is blowing up and he's walking away and being a cool guy and not actually looking at the explosion, explosions typically slow down. You know, you like gas when it goes, like it gets very quick, but then it goes pooh. Explosions don't speed up and just keep speeding up. That's what's happening in the universe, though. The universe is not just expanding, but its rate of expansion is accelerating.
Ever since, so in a real sense, the universe is 13.8 billion years old. That's a big number, kind of hard to think about. A nice way to think about it, though, is to map it onto 1 year. So let's say the universe, it just linearly map the time intervals from 13.8 billion years onto 1 year. So the Big Bang then is on January 1st at 12 a.m. And you wait for quite a long time before the dinosaurs emerge. The dinosaurs emerge on Christmas, it turns out. And
12 months, almost 12 months later.
Getting close to the end, yes.
Getting close to the end.
And the extinction event that let the mammals and ultimately humans inherit the Earth from the dinosaurs occurred on December 30th. And all of human history is a small part of the last day. And so yes, so we're occupying only a human lifetime is a very, very infinitesimal part of this interval of these gigantic cosmic reaches of time. And in space, we can tell a very similar story. In fact, it's convenient to think that the size of the universe is the distance that light can travel in 13.8 billion years. So it's 13.8 billion light years. That's how far you can see out. That's how far things can signals can reach us from, and that is a big distance because compared to that, the universe, the Earth is a fraction of a light second. So again, it's really, really big. And so if we want to think about the universe as a whole in space and time, we really need a different kind of imagination. It's not.
Sorry, I'm gonna cut him. I'm gonna cut him off here, but it's true. Like, you need a completely different conception or imagination of scale and scope. That's why, like, flying through space engines sometimes is really fun, because you get to actually kind of, for a second, like, let your brain realize just how incomprehensibly large the universe that we can see is. And so, sometimes, I always hear, like, people talk about things like, oh, it's $1 billion or $1 million. Like these numbers are almost incomprehensible. It's very difficult for us to even understand what is the actual proportional difference as those numbers get larger and larger and larger. So finding new tools for us to frame that stuff and realize that, like, in the age of all things that ever were, we are just, like, on the tiny speck end of, the beginning.
It's not something you can grasp in terms of psychological time in a useful way. You have to think, you have to use exponential notation and abstract concepts to really get any hold on these vast times and spaces. On the other hand, let me hasten to add that doesn't make us small or make the time that we have to us small, because again, looking at those pictures of what our minds are and some of the components of our minds, these beautiful drawings of the cellular patterns inside the brain, you see that there are many, many, many processing units. And if you analyze how fast they operate, I tried to estimate how many thoughts a person can have in a lifetime. That's kind of a fuzzy question, but I'm very proud that I was able to define it pretty precisely. And it turns out we have time for billions of meaningful thoughts
in a
lifetime. So it's a lot. We shouldn't think of ourselves as terribly small, either in space or in time, because although we're small in those dimensions compared to the universe, we're large compared to meaningful units of processing information and being able to conceptualize.
Again, this is kind of back to what I was saying at the beginning, like, the fact that the human brain is able, just even be a conscious, intelligent, communicative thing, but to be able to control our natural world with such precision that we're able to have the benefits of aeronautics, computers, and all of these other things. It's an incredible testament to just the sheer processing power that's, like, in our heads. So though, yes, we are tiny, infinitesimal objects in the universe, and the time scale in which we occupy is very, very short, what goes through our heads is incredible, and probably, like, a beautiful thing for all organisms to experience in the wonderful galaxy and universe that we float around in.
Yeah, but 99% of those thoughts are probably food, sex, or internet related.
Well,
But yeah,
they're not. That's right.
only like 0.1 is Nobel Prize winning ideas. But
That's true.
I love that.
You
I
know,
love
there's
that
a
Lex
lot
brought
of
it back.
winning Nobel Prize.
how did you do that calculation? Can you maybe break that apart a little bit, just kind of
It's
for
gonna get
fun,
nerdy
in
here
sort
in
of
a
an
second.
intuition of
Yeah.
how we calculate the number of thoughts?
The number of thoughts, right? It's
Oh.
necessarily imprecise because a lot of things are going on in different ways. And what is a thought? But there are several
Hold on,
things
let's
that point
analyze
to
this.
more or less the same rate of being able to have meaningful thoughts. For instance, the one that I think is maybe the most penetrating is how fast we can process visual images. How do we do that? If you've ever watched old movies, you can see that when well, any movie, in fact, that a motion picture is really not a motion picture. It's a series of snapshots that are played one after the other, and it's because our brains also work that way. We take snapshots of the world, integrate over a certain time, and then go on to the next one, and then by post-processing create the illusion of continuity and flow. We can deal with that, and if the flicker rate is too slow, then you start to see that it's a series of snapshots, and you can ask, what is the crossover? When does it change from being something that is matched to our processing speed versus too fast? And it turns out about 40 per second. And then if you take 40 per second as how fast we can process visual images, you get to several billions of thoughts. If you ask what are some of the fastest things that people can do, well, they can play video games, they can play the piano very fast if they're skilled at it, and again you get to similar units. Or how fast can people talk? You get to within a couple of orders of magnitude, you get more or less to the same idea. So that's how you can say that there's billions of there's room for billions of meaningful thoughts.
Yep.
I won't argue for exactly 2 billion versus 1.8 billion. It's not that kind of question, but I think any estimate that's reasonable will come out within, say, 100 billion and 100 million. So it's a lot.
It would be interesting to map out for an individual human being
So my friend wants insight into the flashing cube. I figured out what the flashing cube is. I'm not sure what that is on his desk. It is obviously just a solid metal cube. Maybe it was a gift from someone. It could be like a rare and interesting metal like titanium or whatever. What you will notice is that as Lex speaks, there is a green flash against the cube. And it's more than likely that in front of him, out of camera, he has a small mixing board. If you ever used a mixing board before, you know that they have indicator lights on them, and those indicator lights are usually green. So as he speaks, the little indicator light is leveling, and you're seeing the reflection of that in the cube. This is what tech talks are all about, guys, is solving these mysteries.
Landscape of thoughts that they've sort of traveled. If you think of thoughts as a set of trajectories, what that landscape looks like. I mean, I've been recently really thinking about this Richard Dawkins idea of memes, and just all this ideas and the evolution of ideas inside of one particular human mind, and how they're then changed and evolved by interaction with other human beings. It's interesting to think about. So if you think the number is billions, you think there's also social interaction. So these aren't like there's interaction in the same way you have interaction with particles. There's interaction between human thoughts that are perhaps that interaction in itself is fundamental to the process of thinking. Like without social interaction, we would be like stuck, like walking in a circle. We need the perturbation of other humans to create change and evolution.
Once you bring in concepts of interactions and correlations and relations, then you have what's called a combinatorial explosion. That the number of possibilities expands exponentially, technically, with the number of things you're considering, and it can easily, rapidly outstrip these billions of thoughts that we're talking about. So we definitely cannot, by brute force, master complex situations, or think of all the possibilities in a complex situations. I mean, even something as relatively simple as chess is still something that human beings can't comprehend completely. Even the best players lose, still sometimes lose, and they consistently lose to computers these days. And in computer science, there's a concept of NP complete. So large classes of problems, when you scale them up beyond a few individuals, become intractable. And so that, in that sense, the world is inexhaustible.
And that makes it beautiful that we can make any laws that generalize efficiently and well, can compress all of that combinatorial complexity just like a simple rule. That itself is beautiful.
It's a happy situation, and I think that we can find general principles of the operating system that are comprehensible, simple, extremely powerful, and let us control things very well and ask profound questions. And on the other hand, that the world is going to be inexhaustible. that once we start asking about relationships and how they evolve and social interactions, and we'll never have a theory of everything in any meaningful sense, because
Of everything, truly everything is. Can I ask you about the?
That's an interesting. That's an interesting perspective. I'm not really like surprised by it, but a lot of different people in physics think that a theory of everything is going to revolve around things like string theory, and other like M theory, like I mentioned before. What I was going to say is, it's interesting to hear someone say like, "I don't think we're going to find one."
Big Bang. So we talked about that space and time are really big, but then, and we humans give a lot of meaning to the word space and time in our like daily lives. But then, can we talk about this moment of beginning and how we're supposed to think about it? That at the moment of the Big Bang, everything was like infinitely small, and then it just blew up.
We have to be careful here, because there's a common misconception that the Big Bang is like the explosion of a bomb in empty space that
Right.
fills up the surrounding place.
It is space.
It is, yeah. As we understand.
That's wild to make that distinction, that it's not like necessarily exploding into anything, that it is the thing that it is becoming. Oh, that's a lot of brain power.
It's the fact. It's the fact, or the hypothesis, but well supported up to a point, that everywhere in the whole universe, early in the history, matter came together into a very hot, very dense. If you run it backwards in time, matter comes together into a very hot, very dense, and yet very homogeneous plasma of all the different kinds of elementary particles, and quarks and antiquarks and gluons and photons and electrons and anti-electrons, everything, all of that stuff.
Like really hot.
Really
and
hot.
really dense.
Really hot. We're talking about way, way hotter than the surface of the sun. Well, in fact, if you take the equations as they come, the prediction is that the temperature just goes to infinity. But then the equations break down. We don't really. There are various. The equations become infinity equals infinity, so they don't feel it's called a singular.
They don't give us a lot of insight into what we're actually trying to figure out, and this is one of the issues when you try to apply large-scale physics, ideas of gravity to the world of the very small. Hopefully, guys like this and people who are going to be his successors are going to develop like the different tools and the different methodologies and frameworks for coming up with new ways to solve these equations, so that we don't get infinity equals infinity, or maybe if we do, we actually understand that in a different way. I don't know who the hell is Ang Lee. Like, what is
Singularity, we don't really
know.
know.
Familiar. Why am I missing? Why am I fucking up the Ang Lee reference here?
So you can't really get a sensible idea of what happened before the Big Bang. We don't. So we need different equations to address the very earliest moments. But so things were hotter and denser. We don't really know why things started out that way. We have a lot of evidence that they did start out that way, but since most of the we don't get to visit there and do controlled experiments. Most of the record is very, very processed, and we have to use very subtle techniques and powerful instruments to get information that has survived.
Get closer and closer to the Big Bang.
Get closer and closer to the beginning of things. And what's revealed there is that, as I said, there undoubtedly was a period when everything in the universe that we have been able to look at and understand, and that's consistent with everything, is was in a condition where it was much, much hotter and much, much denser, but still obeying the laws of physics as we know them today. And then you start with that. So all the matter is in equilibrium. And then with small quantum fluctuations and run it forward, and then it produces, at least in broad strokes,
you love Randy Newman.
the universe we see around us today.
Do you think we'll ever be able to, with the tools of physics, with the way science is, with the way the human mind is, we'll ever be able to get to the moment of the Big Bang in our understanding, or even the moment before the Big Bang? Can we understand what happened before the Big Bang?
I'm optimistic, both that we'll be able to measure more, so observe more, and that we'll be able to figure out more.
So to address this guy's point, I think that this is where AI is going to unlock a lot of our understanding of how the universe works. There's actually a really cool story that I thought I bookmarked. Essentially how we found new strings of dark matter generated through AI dark matter. Here we go. So we've been able to use AI essentially to. So I clicked on quite possibly the worst article. Anyway, I'll find it later in another window. But essentially, they were able to use AI to string together and see strings of dark matter because it's really good at recognizing patterns as opposed to human beings. So I think these are the kind of tools that are going to help unlock physicists' ability to study these really, really deep and almost like mind-bending questions.
They're very, very tangible prospects for observing the extremely early universe, so even much earlier than we can observe now.
Yes, Lex is straight up Men in Black.
It might be since they interact so weakly with ordinary matter. Sort of send a minimally processed signal from the Big Bang. It's a very weak signal because it's traveled a long way and diffused over long spaces, but people are gearing up to try to detect gravitational waves that could have come from the early universe.
Yeah, LIGO's incredible engineering project.
Yes.
I want to show you guys LIGO really quickly. It is actually super cool. I was talking a little bit about it earlier on stream. Let's see if I can find a good site for it, like a good resource. One sec. So this is what LIGO looks like. It is essentially these two very long tubes. And inside of these tubes are lasers that are shooting into prisms. And they're like the level of stabilization technology that goes in to make sure these lasers do not move is absolutely insane. And when there are extremely large ripples in the gravitational field, the LIGO detectors are able to detect that. And these were the two things that detected the first, what we think are black holes colliding, is the gravitational waves from those two objects knocking together were so strong that we were able to pick them up from like billions and billions of light years away.
the most sensitive, precise
Yes.
devices on Earth. The fact that humans can
Right.
build something like that is truly awe-inspiring from an engineering perspective.
Right. But these gravitational waves from the early universe will probably be of a much longer wavelength than LIGO is capable of sensing. So there's a beautiful project that's contemplated to put lasers in different locations in the solar system. You know, we really separated by solar system scale differences, like artificial planets or moons in different places, and see the tiny motions of those relative to one another as a signal of radiation from the Big Bang. We can also maybe indirectly see the imprint of gravitational waves from the early universe on the photons, the microwave background radiation that is our present way of seeing into the earliest universe. But those photons interact much more strongly with matter. They're much more strongly processed, so they don't give us directly such an unprocessed view of the early universe, of the very early universe. But if gravitational waves leave some imprint on that as they move through, we could detect that too, and people are as we speak, working very hard towards that goal.
It's so exciting to think about a sensor the size.
Okay,
of
it's
the
the first
solar
comment.
system, like
That would be a fantastic.
there.
I mean, that would be a pinnacle artifact of human endeavor
Pens,
to me. It
taking
would
6
be
pens.
such an inspiring thing that just we want to know. And
Yeah,
we go
it
to
mostly
these
mostly about
extraordinary
pens.
lengths of
Mostly about
making
pens.
gigantic things that are also very sophisticated, because what you're trying to do.
I was about to say, Matt, like, he looks like he was traveling at like Mach 3 and then just stopped, and his hair is still traveling at that speed. It's absolutely insane.
You have to understand how they move. You have to understand the properties of light that are being used, the interference
does let it
between
cover
light.
the Tommy
You
logo.
have to be able to make the light with lasers and understand.
Someone
the
else said that
quantum theory
in
and get
the
timing
comments, Matt.
exactly right. You know, it's an extraordinary endeavor involving all kinds of knowledge, from the very small to the very large, and all in the service of curiosity and built on a grand scale. So. Yeah.
Yeah. So
it'd make me proud to be a human if we did that.
I love that you're inspired both by the power of theory and the power of experiment. So this is both I think are exceptionally impressive, that the human mind can come up with theories that give us a peek into how the universe works, but also construct tools that are way bigger than the evolutionary origins we came from.
Right. And by the way, you know, the fact that we can design such things and they work is an extraordinary demonstration that we really do understand a lot.
And then in some ways,
and it's our ability to answer questions that also leads us to be able to address more ambitious questions.
so
All right, now we're getting the fun stuff. This is where we get into the aliens.
you mentioned that at the Big Bang in the early days, things were pretty homogeneous.
Yes.
But here we are, sitting on Earth, two hairless apes, you could say, with microphones. In talking about the brief history of things, you said it's much harder to describe Sweden than it is the universe. So there's a lot of complexity. There's a lot of interesting details here. So how does this complexity come to be, do you think? It seems like there's these pockets.
Yeah.
We don't know how rare of like where hairless apes just emerge.
Yeah.
And then that came from the initial soup that was homogeneous. Was that is that an accident?
Well, we understand.
Absolutely lost the
We
toupee.
understand in broad outlines how it could happen. We certainly don't understand why it happened exactly.
It almost looks like he just took the toupee and like moved it to the back of his head, and that's what's sticking out the back is just like his, like, you know, kind of like how you put your glasses back on your head. He just did that with his toupee.
In the way it did, but
No disrespect, by the way. This guy is a brilliant scientist, and I shouldn't be making fun of his hair because, like, and actually, you know, fuck you guys too for nah. I'm kidding.
or there are certainly open questions about the origins of life and how inevitable the emergence of intelligence was, and how that happened. But in the very broadest terms, the universe early on was quite homogeneous, but not completely homogeneous. There were part in 10,000 fluctuations in density within this primordial plasma. And
wow. Jay has entered
as
the chat.
time
What up,
goes
Jay?
on, there's an instability which causes
It's the
those
number
density
one
contrasts
observation
to increase.
is his
The
pen
gravitational instability,
issue.
where it's denser, the gravitational attractions are stronger, and so that brings in more matter, and it gets even denser, and so on and so on. So
Yeah.
so
We're gonna
there's a
like,
natural tendency
big
of
chat
matter
night.
to clump
Big chat.
because of gravitational interactions, and then the equations get complicated when you have lots of things clumping together. Then we know what the laws are, but we have to a certain extent, wave our hands about what happens. But basic understanding of chemistry says that if things and the physics of radiation tells us that as things start to clump together, they can radiate, give off some energy, so they slow down. As a result, they lose energy. They conglomerate together, cool down, form things like stars, form things like planets. And so, in broad terms, there's no mystery. There's that's what the scenario. That's what the equations tell you should happen. But because it's a process involving many fundamental individual units, the application of the laws that govern individual units to these things is very delicate, or computationally very difficult, and more profoundly, the equations have this probability of chaos or sensitivity to initial conditions, which tells you tiny differences in the initial state can lead to enormous differences in the subsequent behavior. So physics, fundamental physics, at some point says, okay, chemists, biologists, this is your problem. and then again, in broad terms, we know how it's conceivable that the humans and things like that can how complex structure can emerge. It's a matter of having the right kind of temperature and the right kind of stuff. So you need to be able to make chemical bonds that are reasonably stable and be able to make complex structures. And we're very fortunate that carbon has this ability to make
aliens is coming right up, guys. That's what they're getting to.
And elaborate branchings and things. So you can get complex things that we call biochemistry, and yet the bonds can be broken a little bit with the help of energetic injections from the sun. So you have to have both the possibility of changing, but also the useful degree of stability. And we know at that very, very broad level, physics can tell you that it's conceivable.
Yeah.
If you want to know what really happened, what really can happen, then you have to go to chemistry. If you want to know what actually happened, then you really have to consult the fossil record and biologists. And so these ways of addressing the issue are complementary in a sense. They use different kinds of concepts. They use different languages, and they address different kinds of questions. But they're not inconsistent. They're just complementary. Right.
It's kind of interesting to think about those early fluctuations as our earliest ancestors.
There's a great scene in Star Trek Next Generation where Q takes Picard back to Earth right as the first amino acids were starting to form in this like pool of goo, and basically goes, "Oh, look, nothing happened." And at the end of the episode, like Picard is the reason why life never formed. It's an interesting representation of the process, but Are the hosts eyes opening at all?
Yeah, that's right. So it's hard. It's amazing.
Lex, he
to
opens his
think
eyes
that,
once in a while.
You know,
Lex, remember, so number one, Lex is very Russian. Like, he was born in Russia. He speaks fluent Russian. His father's a Russian physicist. He's a friend of Joe Rogan. He's very into jujitsu and martial arts. But he's also a MIT professor and a very like up and coming, just like leading the master of the field of AI.
this is
But still, he 100% gives murder vibes. I'm not dejecting that for a second.
modern answer to the or the modern version of what the Hindu philosophers had. That art thou. If you ask what, okay, that those little quantum fluctuations in the early universe are the seeds out of which complexity, including plausibly humans, really evolve. You don't need anything else.
That brings up the question of asking for a friend here. If there's, other pockets of complexity, commonly called as alien intelligent civilizations out there.
Well, we
I
don't
hope
know for
I
sure, but
really want someone to send this to Lex.
I have a strong suspicion that the
This
answer
chat's
is yes,
great.
because the one case we do have at hand to study here on Earth, we sort of know what the conditions were that were helpful to life, the right kind of temperature, the right kind of star that maintains that temperature for a long time, the liquid environment of water, and once those conditions emerged on Earth, which was roughly 4.5 billion years ago, it wasn't very long before what we call life started to leave relics. So we can find forms of life, primitive forms of life, that are almost as old as the Earth itself, in the sense that once the Earth was turned from a very hot boiling thing and cooled off into a solid mass with water, life emerged very, very quickly. So it seems that these general conditions for life are enough to make it happen relatively quickly. Now, the other lesson I think that one can draw from this one example. It's dangerous to draw lessons from one example, but that's all we've got. And that the emergence of intelligence
probably on shrooms.
is a different issue altogether.
So yeah, there needs to, when we talk about aliens, there needs to be a distinction between whether we're talking about just alien bacteria that exist or is starting to evolve on another planet, whether there's like plant material, fungus, even just like rudimentary species of worms and whatever you might call a space chicken. But the idea of actual intelligent life that is capable of the same type of technological feats that we are, that's quite the extrapolation. And another thing that they've been talking a little bit about is the cooling of the universe, and the fact that the Earth was able, life formed on the planet Earth because it was able to cool down, liquid water formed. There's all of these wonderful things that spawn that. So we would assume that needs to happen on other planets as well. And the universe is just getting cool enough now for life to emerge. So that's one of the conditions of the Fermi paradox. Like, there might not be any aliens in the universe, or we might be some of the first, because it just got cool enough, and the chaos and the insanity of everything exploding and coming together has just chilled out enough that aliens can start to form. So there's also the possibility that we're some of the first like alien or intelligent life in the entire universe. You never know, guys.
Together, it
could be. We very much could be the forerunners.
And seems to have been pretty contingent. For a long time, well, for most of the history of life, it was single-celled things.
Yes.
Even multicellular life only rose about 600 million years ago, so much after, so and then intelligence is kind of a luxury, if you think. Many more kinds of creatures have big stomachs than big brains, and in fact.
So that's a really actually interesting thing to say. Intelligence is a luxury, because when you think about it, like most animal life on Earth exhibits a certain level of intelligence, I would say that nothing rivals, what humans have been capable of, and we truly do have a very unique luxury in that space, that we are able to have a level of cognition that is cannot be rivaled by anything in the natural world that we know of.
Most have no brains at all.
Also, aliens, if you are in the chat, please say hello. Don't be shy. We will not sell you out to the FBI. There are no men in black here to take you away.
In any reasonable sense. And the dinosaurs ruled for a long time, and some of them were pretty smart, but they were at best bird brains, because birds came from the dinosaurs, and it could have stayed that way, and the emergence of humans was very contingent and kind of a very, very recent development on evolutionary timescales. And you can argue about the level of human intelligence, but it's, I think it's
pretty impressive.
That's what we're talking about, and it's very impressive, and can ask these kinds of questions and discuss them intelligently. So I guess so this is a long-winded answer or justification of my feeling is that the conditions for life in some form are probably satisfied in many, many places around the universe, even within our galaxy. I'm not so sure about the emergence of intelligent life.
So that's interesting. You can already tell he's a little bit of a pessimist in some spaces, because earlier he alluded to whether or not that we'll have a theory for everything, and he's like, probably not. And if it's like, is there going to be intelligent life? Probably not. And I actually tend to agree with him. I think the emergence of, oh shit, he's in the chat, he figured it out, the man is in the chat. Yeah, the emergence of intelligent life is extremely suspect, let alone intelligent life that is able to overcome the physical barriers of the universe. Something to keep in mind, guys, is that the universe is consistently expanding all the time, and it's actually speeding up. So even if you could travel at the speed of light from one point to another, there are parts of the universe that are physically inaccessible to us over time. Yeah, you guys didn't even know about the icon game. This is going to completely, the emotes is going to completely change the game now that our friend Andrew's here.
Or the emergence of technological civilizations. That seems much more contingent and special, and we might. It's conceivable to me that we're the only example in the galaxy. Although, yeah, I don't know one way or the other. I have different opinions on different days of the week.
But one of the things that worries me, in the spirit of being humble, that our particular kind of intelligence is not very special. So there's all kinds of different intelligences. And even more broadly, there could be many different kinds of life.
Yes.
So
it's a really good point. There could be certain patterns of intelligence, certain things that are in other systems right in front of us, like trees or in animal species, that we're just incapable of perceiving. And so, there definitely is the potential for there being intelligent life on other planets, but they could be creatures that are basically comprised of different gases or something, and it would be almost incomprehensible for us to be able to see them, let alone contemplate how they think about their physical universe.
Or the basic definition, and I just had, I think somebody that Sarah Walker, I just had a very long conversation with her about even just the very basic question of trying to define what is life from a physics
Yeah.
perspective.
Yeah.
Even that question within itself, I think one of the most fundamental questions in science and physics and everything is just trying to get a hold,
There we
trying to
go.
get some universal laws around the ideas of what is life, because that kind
Yeah,
of
well-
unlocks a bunch of things around life, intelligence, consciousness, all those kinds of things.
I agree with you in a sense, but I think that's a dangerous question because
Interesting.
the answer can't be any more precise than the question, and the question, what is life, kind of assumes that we have a definition of life and that it's a natural phenomena that can be distinguished, but that really there are edge cases like viruses, and some people would like to say that electrons have consciousness, and so you can't, if you really have fuzzy concepts, it's very hard to reach precise kinds of scientific answers. But I think there's a very fruitful question that's adjacent to it, which is has been pursued in different forms.
Someone please
for,
think of the electrons, the poor
quite a while,
electrons and their consciousness.
and is now becoming very sophisticated in reaching.
Guys, when you think about it, we are enslaving electrons. Like it is a genocide on electrons right now in terms of what we do to them and what we're putting them through.
New directions, and that is, what are the states of matter that are possible? So in high school or grade school, you learn about solids, liquids, and gases, but that really just scratches the surface of different ways that are distinguishable, that matter can form into macroscopically different meaningful patterns that we call phases of matter. And then there are precise definitions of what we mean by phases of matter, and that have been worked out and fruitful over the decades. And we were discovering new states of matter all the time and kind of having to work at what we mean by matter. We're discovering the capabilities of matter to organize in interesting ways.
In my last stream, I was talking a little bit about the Vendenstein 7 fission reactor and how it uses plasma, which is another state of matter, which is kind of it's I don't actually know how to describe it. I should really pull up a video because I'm going to do a terrible job of it, but this is why these pursuits in physics are so important, because they help us better understand our natural world and make us give us some capacity to be able to derive great value, whether it's through computational power or whether it's through just the production of energy.
And some of them, like liquid crystals, are important ingredients of life. Our cell membranes are liquid crystals, and that's very important to the way they work. Recently, there's been a development in where we're
Fusion
talking
is
about
so hot right now.
states of matter that that are not static, but that have dynamics, that have characteristic patterns not only in space but in time. These are called time crystals, and that's been a development that's just in the last decade or so. It's really flourishing.
Was that with the that was the what the fuck is it called? China fusion reactor. What's artificial sun? Let's see here. Process reactor sun staining to the previous. Oh, are you gonna really do this to me? Terrible website. Fuck this shit. Anyway, yeah. China's pushing fusion hard right now. I've heard there's a reactor. I was did a video on this last week. I can't remember the name of it, but we can come back to it. It's super sick.
And so.
Here, I'll find it.
Is there a state of matter that or a group of states of matter that corresponds to life? Maybe, but the answer can't be any more definite than the question.
I mean, I got to push back on those are just words. I mean, I disagree with you. The question points to a direction. The answer might be able to be more precise than the question, because just as you're saying, there's that we could be discovering certain characteristics and patterns that are associated with a certain type of matter, macroscopically speaking, and that we can then be able to post facto say, this is, let's assign the word life to
Oh,
this
shit,
kind of
Landmasters.
matter.
I
Enter
agree
the
with
chat,
that
respect.
completely. That's so it's not a disagreement. It's very frequent in physics that
I do like that. Like Lex does actually challenge his his people here. Oh, this is
or
great.
in science that
The fuck-
words
yeah, where
that
does
are in
crowns come
common
from?
use get
Guys, what's sick is that if I can get now up to 50 followers, I'll be able to make my own emotes, and that'll be a lot of fun.
refined and reprocessed into scientific terms. That's happened for things like force and energy, and so in a way, we find out what the useful definition is, or symmetry, for instance, and the common usage may be quite different from the scientific usage, but the scientific usage is special and takes on a life of its own, and we find out what the useful.
Guys, I need you to get like hardcore MLM. I know you're all part of my network, but you guys need to go out and build your networks. Okay, I need to see you guys out there driving this stream and telling your network of people that if they get in on your level, they're gonna realize the benefits down the road. We got a fucking hardcore like culty MLM this chat.
Version of it is what the
No, you can't. I have to get to
the
50
fruit
followers before I can
version
do
of it
that.
is. So I do think, so in that spirit, I think if we can identify states of matter or linked states of matter that can carry on processes of self-reproduction and development and information processing, we should say we might be tempted to classify those
As life.
things as life. Yeah.
Well, can I ask you about the craziest one, which is the one we know maybe least about, which is consciousness? Is it possible that there are certain kinds of matter would be able to classify as conscious, meaning like so there's the panpsychists, right, or the philosophers
Yeah.
who kind of try to imply that all matter has some degree of consciousness, and
Yeah.
you can almost construct like a physics of consciousness.
Yes.
Do you again, we're in such early days of this, but nevertheless it seems useful to talk about. Is there some sense from a physics perspective to make sense of consciousness? Is there some
Well,
hope?
again, consciousness is
Imprecise.
a very imprecise word and loaded with connotations that I think we don't want to start a scientific analysis with that. I don't think. It's often been
This is gonna get
important
interesting.
in science to start with simple cases and work up. Consciousness, I think what most people think of when you talk about consciousness is, okay, what am I doing in the world? This is my experience. I have a rich inner life and experience and where is that in the equations? And I think that's a great question, a great question. And actually, I think I'm gearing up to spend part of to try to address that in coming years.
One version of asking that question, just as you said now, is what is the simplest formulation of that to study?
I think I'm much more comfortable with the idea of studying self-awareness as opposed to consciousness, because that sort of gets rid of the mystical aura of the thing. And self-awareness is in simple, I think contiguous, at least, with ideas about feedback. So
I was literally just thinking that word before he said that. Like self-awareness is quite literally just a feedback system that allows you to iterate. And in one of my previous videos, when I was doing a video on artificial intelligence, they explained the concept of back propagation and how that really changed the game for AI when it could send information back through the network and then rehash it based off what it learned. And they kind of said like, oh, neurons don't do this. I'm like, no, they very much do.
If you have a system that
Also,
looks at its own state and
R.I.P.
responds to it,
Landmaster for the
that's
band.
a kind of self-awareness. And
That's hilarious.
more sophisticated versions
Absolutely
could be
hilarious.
like in information processing things, computers
Respect.
that look into their own internal state and do something about it. And I think that could also be done in neural nets. This is called recurrent neural nets, which are hard to understand and kind of a frontier. So I think understanding those and gradually building up a kind of profound ability to conceptualize different levels of self-awareness. What do you have to not know, and what do you have to know, and when do you know that you don't know it, or what do you think you know that you don't really know? And these, I think, clarifying those issues. When we clarify those issues and get a rich theory around self-awareness, I think that will illuminate the questions about consciousness in a way that, scratching your chin and talking about qualia and blah 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 is never going to do.
Well, I also have a different approach to the whole thing. So there's from a robotics perspective, you can engineer things that exhibit
Yes.
qualities of consciousness without understanding
Well,
how things work, and from that perspective, you it's like a back door,
Yeah.
like enter through the psychology door.
precisely.
The cognitive science door.
I think we're on the same wavelength here. I think that, and let me just add one comment, which is, I think we should try to understand consciousness as we experience it, in evolutionary terms, and ask ourselves why. Why does it happen?
This thing seems useful. Why is it useful?
Why is it useful? I think we've got a conscious eye watch here. Interesting question. Thank you, Siri. Okay.
Talking about consciousness, and his eye watch is like, yes, hi, I'm here.
I'll get back to you later.
Clever girl.
And I think what we're going, I'm morally certain that what's going to emerge from analyzing recurrent neural nets and robotic design and advanced computer design is that having this kind of looking at the internal state in a structured way that doesn't look at everything. It's encapsulated, looks at highly processed information, is very selective, and makes choices without knowing how they're made. So there'll also be an unconscious. I think that is going to turn out to be really essential to doing efficient information processing, and that's why it evolved, because it's helpful, and because brains come at a high cost. Yeah.
So there has to be a good why.
And there's a reason. Yeah, they're rare in evolution. Big brains are rare in evolution, and they come at a big cost. I mean, if they have high metabolic demands. They require very active lifestyle, warm-bloodedness, and take away from the ability to support metabolism of digestion, and so it comes at a high cost. It has to pay back.
Yeah, this is why you have species of animals and even insects, like incredibly simple creatures that can go through things like being frozen and come back, because they have very simple systems that are very rugged and can hold up to a lot of abuse. Whereas, obviously there are trade-offs in evolution for these things.
I think it has a lot of value in social interaction. So I actually am spending the rest of the day today with our friends that are our legged friends in robotic form at Boston Dynamics. And I think so. My probably biggest passion is human-robot interaction, and it seems that consciousness from the perspective of the robot is very useful
Yes.
to improve the human-robot interaction experience. The display of consciousness, but then to me there's a gray area between the display of consciousness and consciousness itself. If you think of consciousness from an evolutionary perspective, it seems like a useful tool in human communication. So
Yes, it's certainly, well, whatever consciousness is will turn out to be.
Yeah.
I think addressing it through its use
yes,
and working up from simple cases and also working up from engineering experience in trying to do efficient computation, including efficient management of social interactions, is going to really shed light on these questions, as I said, in a way that sort of musing abstractly about consciousness never would.
So, I think there's an interesting, and I don't know if any of you guys were around for one of my previous streams where I was talking about artificial intelligence, but AI playing game. There's this incredible study on OpenAI using, I think it was like Google OpenAI, and I'll just let this video speak for itself. It's about 6 minutes. I'll try
Scholars, this is 2-minute papers with
uninterrupt as
Karo
much as
Zona
possible.
Fehir. In this project, OpenAI built a hide-and-seek game for their AI agents to play. While we look at the exact rules here, I will note that the goal of the project was to pit two AI teams against each other and hopefully see some interesting emergent behaviors. And boy, did they do some crazy stuff.
So what we're looking for is, again, interesting emergent behavior from simple systems that have very simple rules.
The coolest part is that the two teams compete against each other, and whenever one team discovers a new strategy, the other one has to adapt. Kind of like an arms race situation, and it also resembles generative adversarial networks a little. And the results are magnificent, amusing, weird. You'll see in a moment. These agents learn from previous experiences, and to the surprise of no one, for the first few million rounds, we start out with pandemonium. Everyone just running around aimlessly. Without proper strategy and